All right, so this is going to be a video all about how the sum from 1 to infinity, n equals 1 to n equals infinity, of 1 over n is actually equal to infinity. So basically I have this right here in the orange. So I'm going to be talking all about how this idea actually came to be, the proof behind it. It's very non-intuitive to think of it as you're adding smaller and smaller numbers, but somehow it's going to infinity. And I'm going to be comparing it to this series right here, which is a geometric series, 1/2 plus 1/4 plus 1/8 and so on. It's just 1 over 2 to the n as the sum of that as n equals 1 to infinity, and it's equal to 1. So we're going to use this fact to basically prove this over here is actually equal to infinity. It's going to be part of that proof. First thing I want to talk about is the non-intuitiveness of this idea. Okay, you're adding smaller and smaller numbers here and it becomes 1. One thing that's interesting about this is if you take the limit of the nth term, so this right here, it's taking the limit as n goes to infinity of the infinitieth term, it's approaching 0, because if you notice it's getting smaller and smaller as you go from one number to the next. And if you kept going with that, if you put infinity in here, it's 1 over 2 to the infinity. If you could actually do that, it would be a very tiny number. If you had one pizza and you divided it by infinitely many people, and it's actually more than infinity, it's 2 to the infinity number of people, each person would basically be getting no pizza. So that's where this 0 comes from for this. Okay, now if you compare this to the 1 over n, remember the sum of this goes to infinity. Again, we're going to prove that in a little bit. I just want you to believe me for now, I guess. That's equal to infinity. The same property happens with this one. The limit as n approaches infinity of 1 over n is also equal to 0. If you have one pizza and you're dividing it by infinitely many people, each person is essentially going to get no pizza. So both of them have a limit where the infinitieth term is approaching 0. This one right here also approaches 0. The other one over here approaches 0. Here's a graph of both of them, and I color coded it for orange and red. This orange one right here is the 1 over n. It's not the sum of 1 over n, it's just 1 over n. And as you can see, it flatlines down to 0, and the red is that 1 over 2 to the n. As you can see, it also approaches 0. So both of these limits do work out. This one ends up being 0. This one ends up being 0 as well. Yet one ends up with a sum of infinity. The other one ends up with a sum of 1. Let's look at this sum of 1 really quick, because I think that part of the reason why it's called a geometric series is you can actually draw this geometrically, and that's what this represents right here in this pink. If you notice, this is a square, and the dimensions of this square, essentially this is right here, this is 1. Okay, you can kind of see this is 1/2, which means this is also 1/2 here. Okay, same thing here, from here to here is also 1. Okay, well, the area would just be base times height, or in this case, base squared, because the base and the height are the same thing. And the area of this is equal to 1. And if you notice, if you add up all these little areas, you also end up getting 1. Okay, so this part right here represents the 1/2, and you can kind of just see it's 1/2 times 1, so it's base of 1/2 times 1 here. So this right here is 1/2. So I'll write that like this. That's 1/2. Okay, here's the 1/4 right here, because it's basically just 1/2 by 1/2, so this is 1/4, so it's 1/2, this whole thing right here, plus 1/4. This part right here represents the 1/8. You can kind of see my dimensions of where I'm getting these numbers from. If you wanted to, you can calculate them yourself. This one right here is going to be half of that, so this is basically going to be the 1/16 right here. It's half of this part right here, and so on. It gets smaller and smaller, and I'm going to run out of room, but you can kind of see that the area ends up being equal to 1 if you sum all of these up, and that's what essentially I was doing up here. 1/2 plus 1/4 plus 1/8, so on. That's what this is doing right here, and it makes sense. It can't get any bigger than this. It just caps out at 1. Okay, now let's compare that to our 1 over n. Okay, again, I already told you in that orange that it's equal to infinity, so it's kind of a spoiler, but we're going to show how that actually comes to be, because this isn't just about the answer. It's actually about thinking about what the answer represents. And like, think about how non-intuitive this is. In our brain, it makes sense to think, well, this one probably ends up just being a finite number as well. Like the other one was equal to 1. This one shouldn't be equal to infinity, yet it is, which is really weird. And I set up a proof here that kind of helps explain it a little bit more. So hopefully this helps. Okay, so let's look at this purple line. Okay, right here it says S sub nu. Okay, this is basically just the new sum that we're looking at. Okay, I made this up based on this sum right here. So we have this sum right here of 1 over n as n equals 1 to infinity, and you have this right here. And I lined it up this way on purpose. Okay, if you notice, the 1 and the 1 match. Okay, the 1/2 and the 1/2 match. Now this one, the 1/4 and the 1/3 do not match, and I did that on purpose. I put two 1/4s here. So there's a 1/4 here, and then there's this 1/3. I just made it a 1/4 in my S new. So you can think about this as like the S old. All right, this is the old sum. This is going to be the new sum. Now, if you notice this 1/3 here, I turned it to 1/4. These two 1/4s end up being 1/2. Okay, so we have 1/2 here, we have 1/2 here. Okay, I'm going to do the same thing over here. This one's equal to 1/8, and then all of these right here, I just turned into 1/8 for my new sum. I didn't actually turn it into it for this sum of 1 over n. I just did it for this S new right here. Now the reason I did that is if you notice this 1/5, 1/6, 1/7, they all turn to 1/8 for this S sub new. And if you notice this purple right here is always going to be less than this orange. And the reason why is because everything got downgraded. Okay, we have right here, we have this 1/3 and it went down to a 1/4 for our new sum. This 1/5 went to a 1/8. This 1/6 went to a 1/8. This 1/7 went to a 1/8. Okay, all of those are going to be less than the value that it is in the orange. Okay, in this sum of 1 over n, it's going to be less than it. Okay, 1/5 is bigger than 1/8. 1/6 is bigger than 1/8. 1/7 is bigger than 1/8. 1/8 is equal to it. But you should be able to see that this S sub new is less than this original sum here. Okay, let's explore this S sub new a little bit more here. Okay, essentially what I'm doing is I'm grouping things into 1/2s. Okay, the 1/2 is right here. Awesome. This 1/4 and this 1/4 become 1/2, which is, I already said this. That's that 1/2 here. Okay, 4 1/8 is 4/8, which is 1/2. And that's this 1/2 here. And I can just repeat this over and over again. I just didn't feel like writing it out, but I can have, let's see, there's 1 1/2 here, there's 2 1/4s, and then there's 4/8. You can kind of follow this pattern, 1, 2 to 4. It's just doubles each time. I would need 8 1/16. Or you can also just think about it, 8/16 is 1/2. I just didn't feel like writing 8 1/16 just because you get the idea. But anyway, what we're doing here is we're adding 1 plus a 1/2 plus a 1/2 plus another 1/2. It's just infinitely many 1/2s. So you can see if there's infinitely many 1/2s, your sum ends up being infinity based on what I just showed right here. 1 plus infinitely many 1/2s is going to be infinity. Okay. Now, what I said before was S sub new is going to be less than this sum right here. Okay, because I downgraded everything. I had the 1/3 downgraded to 1/4, 1/5, 1/6, 1/7. It's going to be less than it. Okay, if I did the 1/16, those would all be less than it as well. Like 1/9 would be greater than 1/16. 1/10 would be greater than 1/16 if I kept going. So you can kind of see that S sub new is actually less than the sum of 1 over n. As n equals 1, this should be a 1 here. That's a typo. To infinity. So if S sub new is always less than this sum of 1 over n, and this one goes to infinity, this one has to be more than infinity. Well, you don't really need to worry about being more than infinity, it's just a bigger infinity. And because it's a bigger infinity, it still goes to infinity, which proves our orange step that we had originally. That if you add up the 1 over n as n equals 1 to infinity, you will get infinity. And it's proven based on the fact that this S sub new, which is less than it, goes to infinity. If the sum of 1 over n is greater than it, then it has to go to infinity as well. And that's basically what it says right here. Because S sub new is always less than the sum of 1 over n as n goes from 1 to infinity, that's embarrassing, that's supposed to be a 1. And S sub new diverges, so since this diverges, it goes to infinity, then the thing that's smaller than it, this one's smaller than this right here. Because this one's small and it goes to infinity, this one's bigger than it, it also goes to infinity, so it must also diverge. Now you cannot do this same thing with this geometric here. You can't downgrade it each time and add up infinitely many 1/2s or infinitely many whatever other number that you want to think of. You cannot do that with that. But if you want, I would definitely try to break this down into something that's going to be less than it each time, and that something also has to diverge itself. Okay, if you notice, my S sub new diverged. So try to do that with the 1 over 2 to the n and try to figure out some way where it can diverge, even though 1 over 2 to the n does converge to 1. It's kind of a fun exercise, even though you kind of already know the answer, you know that it's not going to work out, but it is still good to try. It is still good for a learning exercise. So basically this whole thing proves that the sum of 1 over n as n equals 1 going to infinity is equal to infinity, even though it doesn't really make sense and you think it would behave the same way as the sum of 1 over 2 to the n as n equals 1 to infinity. So that's basically a proof of how that all works. Hopefully your mind is blown, because I know mine is. I've been teaching this for a while and I'm still amazed by this fact. It's just, it's crazy to me. So that's proving that the sum of 1 over n as n equals 1 to infinity goes to infinity itself. If you have any questions about anything in this video, let me know.